Welcome back to the deep dive.
Great to be here.
Today we're kicking off something really special. It's for all you aspiring welding inspectors out there. Our brand new CSWIP 3.1 exam preparation series.
Yep, jumping right into it.
Think of this as your, let's say, shortcut to building that foundational knowledge you really need. Not just for the exam, but, for a successful career.
Absolutely. And look, this isn't just about memorizing facts for a test.
Right.
Understanding these fundamental welding principles.
Yeah.
That's about making smart, safe decisions out in the field.
Yeah.
You need clear, accurate knowledge. It really underpins everything an inspector does.
Couldn't agree more. So for this deep dive, our mission is pretty straightforward. We're going to unpack some key multiple choice questions.
Since they pop up often.
Exactly. The ones you're likely to see on the CSWIP 3.1 exam. We'll break down the answers, sure, but also the why behind them. Help you really solidify these essential concepts.
Get that core understanding locked in.
Let's just jump right in then. First question. It's about mechanical testing. A real cornerstone, this one.
Fundamental stuff.
Okay, here it is. A transverse tensile test from a weld procedure approval record, WPAR test plate, is used to measure. And the options are A, tensile strength of the weld, B, tensile strength of the joint, C, stress-strain characteristics of the weld, D, stress-strain characteristics of the joint.
Okay.
So a transverse tensile test. Sounds simple enough, but I've heard different takes on what it's really measuring in this context. For a WPAR, are we just looking at the weld metal, or is it broader?
That's the key distinction right there. And it's fascinating because this test gives you a holistic view.
Okay.
The correct answer is B, tensile strength of the joint. And it's crucial because the WPAR, the whole point is to qualify the entire welding process, not just the filler metal, right?
Right, the whole procedure.
Exactly.
Right.
So when you pull that transverse sample, you're stretching the weld metal, yes, but also the HAZ.
The heat-affected zone.
Correct, on both sides, and bits of the parent material. The test basically finds the weakest link across that whole section.
So it's not just about how strong the weld bead itself is.
Not at all. I mean, you could have super strong weld metal, but if the heat from welding has made the adjacent parent material, the HAZ, brittle, well, that's where it's going to fail.
Okay, that makes sense. The joint fails even if the weld is technically strong.
Precisely. That's the critical point. The test checks the performance of the entire assembly under tension. So options just focused on the weld or general stress-strain characteristics aren't quite hitting the main purpose of this specific test for WPAR. It's about the overall joint strength.
So practically speaking, for an inspector, that means looking beyond just the surface appearance.
Absolutely. Visual is important, but it doesn't tell you about potential weakening in the HAZ. This test forces you to consider the impact of the welding process on everything involved. It's a fundamental check.
Got it. Holistic performance. That's a great takeaway. Okay, let's switch gears a bit. Materials. Specifically, stainless steels.
The stainless family. Always interesting.
Right. So many types. Here's the question. With reference to the various grades of stainless steels, which of the following statements is true? Options. A, they are all non-magnetic. B, they all require 100% R for GMAWC. They all have very high thermal conductivity. D, only certain grades can be used for service at very low temperatures.
Okay.
Stainless steels. It feels like a huge topic.
Yeah.
Lots of potential pitfalls. What's the definitive truth among these options, especially thinking about, say, really cold conditions?
Yeah, it's a big family, and knowing the differences is vital, especially for critical stuff. The correct answer here is D. Only certain grades can be used for service at very low temperatures.
Okay, why that one?
Well, think about the different types: austenitic, ferritic, martensitic, duplex. They all have different structures inside, different metallurgy.
Right.
That structure dictates properties, like magnetism option A. Many people think all stainless is non-magnetic.
I might have thought that.
A lot of people do. But it's mainly the austenitic grades, like your common 304 or 316, in their normal state. Ferritic and martensitic stainless steels, they're definitely magnetic, so A is out.
Okay.
Option B, shielding gas for GMAW or MIG-MAG welding, 100% argon. Sometimes yes for some grades, but often you're using mixes argon with CO2 or helium or even a bit of oxygen, depending on the specific stainless is what you're trying to achieve. So B isn't universally true.
Makes sense. Different recipes for different metals.
Exactly. And C, high thermal conductivity? Actually, no. Compared to regular carbon steel, stainless steels generally conduct heat less well. So C is wrong too.
Lower conductivity. Okay.
Which brings us back to, it's your picks, low temperatures. Cryogenic stuff like LNG tanks. Here, the material choice is absolutely critical. Austenitic stainless steels, because of their crystal structure, stay tough and ductile even when incredibly cold.
So they don't become brittle.
Right, they maintain their toughness. But ferritic and martensitic grades, they can become very brittle at low temperatures. Using the wrong grade in that kind of application could be catastrophic.
Yeah.
So yeah, only certain grades are suitable. An inspector has to know this.
Yeah, you can see the massive safety implications there. Choosing the wrong material doesn't bear thinking about. Okay, let's move to question 3. This one's about terminology.
Always important to use the right language.
When two different material types are welded together, the joint is referred to as options. A composite joint. B, a transition joint. C, an autogenous weld. D, heterogeneous joint. So welding steel to aluminium or stainless to carbon steel, what's the proper industry term?
The correct specific term we use in welding is B, a transition joint.
Transition joint, okay.
Yeah, it specifically means joining dissimilar metals.
Yeah.
And it flags up that there are often special challenges involved.
Like what kind of challenges?
Well, different metals expand and contract at different rates when heated and cooled, right? So you can get high stresses building up.
Leading to cracks, potentially.
Potentially, yes. And also, metallurgically, the metals might not mix well. You could form brittle phases like intermetallic compounds right at the interface where they join. That weakens the whole thing.
So you need special procedures, maybe special filler metals?
Often, yes. You need a filler that can bridge the gap, metallurgically speaking. Now, looking at the other options, C, an autogenous weld, just means no filler metal was used. Could be same or different materials.
Okay.
And the D, heterogeneous joint, is sort of a general term for any joint made of different stuff. But in welding, when we join two different metal types specifically, transition joint is the precise term everyone understands. It signals those specific challenges.
Got it. Precision in language reflecting precision in engineering. Okay, let's shift to a process question. MIG-MAG welding, specifically dip transfer.
Short-circuiting, the workhorse.
Exactly. Question 4. The dip transfer, or short-circuiting mode of metal transfer used for MIG-MAG welding, is characterized by options. A, giving deep penetration. B, being suitable for positional welding. C, giving low spatter. D, giving high deposition.
Right.
Dip transfer is everywhere. What's its key feature, the thing that makes it so useful?
The standout characteristic, and the correct answer, is B, being suitable for positional welding.
Positional. Okay, why is that?
It's all about how the metal transfers. In dip transfer, the wire actually touches the weld puddle, dips in creating a short circuit. Then the arc reignites briefly, melts off a drop of metal, and the cycle repeats very fast.
Okay, dipping in and melting off.
Right. The key consequence is relatively low heat input and a small, quite controllable weld puddle.
Controllable.
Exactly. That smaller, cooler puddle doesn't want to drip or sag as much as a big hot puddle. That makes it great for welding vertical up or overhead or horizontally. You can manage the molten metal against gravity.
So welding pipes in position or overhead structures?
Perfect for that. Also good for thinner materials where you don't want too much heat and for bridging gaps. Now, the other options, A, deep penetration. Nope, dip transfer is generally lower penetration compared to, say, spray transfer.
Right.
C's low spatter. Well, it can produce spatter, especially if not set up right. Maybe less than older methods, but modes like pulse spray are generally considered lower spatter. And D-rot, high deposition. Again, no, that's more characteristic of spray transfer. Dip transfer is more about control than speed or volume.
Control over deposition rate. Makes sense. Okay, final question for this session. Let's talk NDT non-destructive testing, specifically ultrasonic testing.
UT, a powerful tool.
Question 5. Ultrasonic testing has an advantage over other NDT methods for the detection of options. A, lack of sidewall fusion. B, root undercut. C, incompletely filled groove. D, root concavity.
Okay, where does UT really shine?
Yeah, what's its forte when it comes to finding those hidden flaws?
Its big advantage, and the correct answer is detecting a lack of sidewall fusion.
Lack of sidewall fusion. Why is UT good for that?
Think about how UT works. You send high-frequency sound waves into the material.
Right, like sonar.
Kinda, yeah. These waves travel through the metal and bounce back when they hit something different, a discontinuity, a flaw. Now, lack of sidewall fusion is basically where the weld metal hasn't fused properly to the side of the joint preparation. It's a gap, often internal.
Hidden inside the weld.
Exactly. And it's typically a planar defect, meaning it's relatively flat, like a crack. These flat internal surfaces are excellent reflectors for ultrasonic waves, especially when the sound beam hits them somewhat perpendicularly. UT is really sensitive to these kinds of flaws, even deep inside the material.
Ah, so it's good at finding those flat internal gaps.
Precisely. Now look at the others. Root undercut, incompletely filled a groove, root concavity. These are generally surface breaking or near-surface issues related to the weld profile.
Things you might even see visually or pick up easily with other methods.
Often, yes. Visual inspection, maybe magnetic particle testing or penetrant testing, are usually better suited or more straightforward for detecting those kinds of surface or shape irregularities. UT can sometimes find them, but it's not its primary strength compared to finding internal cleaner flaws like lack of fusion or cracking.
So it highlights using the right NDT method for the suspected type of flaw.
Absolutely. They complement each other. No single method finds everything perfectly. You choose the tool based on what you're looking for and where you expect it to be.
That's a critical point for any inspector. Great. Wow, okay, we've covered quite a bit there. 5 key questions right from the CSWIP syllabus.
Good foundational topics.
I really hope this focused discussion, digging into the why, gives you listening a real confidence boost for your exam prep.
Yeah, and remember, it's not just about passing. It's about understanding. That's what makes a good inspector. Knowing why that's the right answer translates directly to better decisions on the job.
Absolutely. And maybe a final thought to take away. As you continue studying, try to connect these principles we've talked about: joint strength, material properties under different conditions, defect detection, to real-world structures.
Think about the consequences.
Yeah, how could understanding, say, transition joints or the limitations of dip transfer actually impact the safety and reliability of a bridge or a pipeline or a pressure vessel? It really brings it home. It's not just theory. It's about preventing failures and ensuring safety.
Well said. It's critical work.
It really is. Well, thank you so much for joining us on this deep dive. Keep learning, keep asking questions,
Keep studying.
and we'll catch you on the next one.